Today's screencast is on partially miscible liquid-liquid extraction. I'll give you a second to pause this and to read over the problem statement. What we have is a stream of acetic acid and water that's being fed in one end of a countercurrent extraction process. The other end, we're feeding a solvent that has a little bit of acetic acid in it. And we know what the exiting raffinate stream should contain, which is 5 weight % acetic acid. I think the first thing to do here is to determine what your solvent is, what your solute is, and what our diluent is. The thing we're trying to clean up is acetic acid. We know that the exiting raffinate stream should contain 5 weight % of acetic acid. That means that acetic acid is going to be our solute, and we'll designate that with an A. We are given what the solvent is. We see that the solvent is 99% isopropyl ether. So isopropyl ether is our solvent, and we'll designate that with an S. That means that water is going to be our diluent, and we'll designate that with a D. So I think that the next thing to do is to plot our equilibrium data, because we're not given a plot of the data, we're just given the weight percents in the water phase and the isopropyl ether phase. So let's do that next. Here's the data that we've been given. We've got the water phase and the isopropyl ether phase. And we already said that isopropyl ether is our solvent. And so this means this is going to be the extract stream. The extract is rich in solvent. So this is going to be our extract. So there is not very much diluent. And this side is going to be our raffinate. We always plot it so that the extract is on this side and the raffinate is on this side, because we always plot the solute A versus the diluent D. So the diluent is down here and the solute is right here. Now I want to combine all of this data so that it's all in one big line here. Here. So this is my diluent and this is my solute. And I take the values from here and I've just reversed the order. So these are here. This 0.52 is down here. This 0.0018 is down here. So I'm going to plot the diluent on the x-axis and the solute on the y-axis. And I'll get this nice little curve that'll look like this, and this part of it will be the extract, and this part of it will be the raffinate. So we plotted our equilibrium data. Why don't we get to the meat of the problem? I'm going to draw a diagram for kind of what's happening here. This is going to be for a multi-stage process. So we're going to have the feed going in one end, and we're going to have the solvent, extract, going in the other end. So the feed is going to come in here, and the feed is F, that equals Rn plus 1, and that equals 1,000 kilograms per hour. This is stage 1, and here we have stage 2. We also know what the composition of the feed is. It's XA on stage n plus 1 equals 0.3, and XD on stage n plus 1 equals 0.7. And let's just remind ourselves that the acetic acid equals A, it's the solute, the water is the diluent, it equals D, and the isopropyl ether equals S, it's the solvent. So we know what our feed is. We're going to label our other feed lines. Here we have Rn, and here we have R1. Another piece of information we're given is that the exiting raffinate stream should be 0.05 acetic acid. So XA of stage 1 equals 0.05. Let's now talk about the solvent streams. The solvent coming in, E naught equals S, we call it both things, equals 1,000 kilograms per hour. And we know the composition of this. The solvent is 99% isopropyl ether and 1 weight % acetic acid. So YA of 0, stage 0, equals 0.01, and y of diluent of stage 0 equals 0, because the remainder of the stream is solvent. There's no diluent in the solvent stream. Let's label our other solvent streams. Here we've got E1, and here we've got En. So that pretty much takes care of labeling our diagram. Let's see which points we can plot just with the information given on our equilibrium diagram here, our ternary diagram. Let's see, we can plot E0, and that's going to be just at 0 and 0.01. So where right there is E0. We can plot the feed, which equals Rn plus 1, and that is at 0.7 and 0.3. Note that we have plotted the solute A versus the diluent D. So 0.7 and 0.3 gives us right here, and that's Rn plus 1. Another point we know is R1, and for that point we know that XA1 equals 0.05. Well, let's talk about this for a second. This is the raffinate stream. That means it's going to be high in diluent and not going to contain very much solvent. Remember, the raffinate is on this side, is on the right side, and the extract, which is high in solvent and does not have much diluent in it, is on this left side. So the raffinate coming out of stage 1 is going to be in equilibrium with the extract coming out of stage 1. So that means it's going to be on the equilibrium curve. So if XA1 equals 0.05, it can either be on this side or this side. It will be on this side because the raffinate will have a large amount of diluent in it. So this is R1. And let's also note that E naught and Rn plus 1 do not have to be on the equilibrium curve because they're not necessarily saturated. They can be any type of stream. Only streams that come out of a stage have to be on the equilibrium saturated curve. So we can connect some of these. We can connect Rn plus 1 and E naught. Rn plus 1 and E naught. Both of these streams are going into the process. So we can sort of think of this as two streams go in and are mixed. So we have a mixing point. And the mixture equals E naught plus Rn plus 1. Both of these streams are going into the process. So they go in and are mixed. We also have X, and we'll do this for the solute. So XA of mixing times M equals YA naught times E naught plus XA n plus 1 times Rn plus 1. Well, let's solve what this XAM is. XAM equals YA naught, which is 0.01 times E naught, which is 2500, plus XA n plus 1, which is 0.3, that's the amount of solute going in the feed, times the feed, Rn plus 1, which is 1000. Oh, I said the solvent is 1000. Whoops. The solvent is 2500. Sorry about that. And we divide it by the mixture, which is going to be 1000 plus 2500. So XAM equals 0.093. So if we go on our plot, we have 0.093, and it has to be on the mixing line. We can see that this point is the mixing point. And if you want to check to see if that's right, you can do a mass balance over the diluent. So the diluent, XDM, equals YD naught times E naught plus XD n plus 1 times Rn plus 1 over the mixture, which is E naught plus Rn plus 1, and that equals 0 times 2500 plus 0.7 times 1000 over 1000 plus 2500, and that equals 0.2. We find that that's kind of what we had here. So this is x d of m, and kind of here is x or y a of m. Now we can use our mixing point to determine where our En is, because we know that the mixture also equals the stuff that comes out. So the mixture equals R1 plus En. That means that R1m and En will all be collinear. And I also know that En will be saturated, so it's got to be on the saturated curve. So I'm going to draw a line between these, and I will have En right here. Alright, so now I know the compositions of all of my streams coming in and out of the process, but I don't know anything about the streams that are internal to the process. The difference between passing streams, so a passing stream would be R1 and E naught, or R2 and E1, or Rn plus 1 and En for this diagram. The difference between these is always the same, and the difference is delta. And the way you can get this delta is by knowing that R1, E naught, and delta are all collinear. So I'm going to draw a line between R1 and E naught, and so imagine that goes through all those. I know that the difference point is somewhere along this line, but I don't know where. But I do know that the difference line is also collinear with Rn plus 1 and En. So I can draw a line between those points, and I know that the difference point is somewhere along that line as well. It's going to be the same difference point in both cases. So where these two lines cross has to be the difference point. So that's my difference point delta. Now I can pretty easily step off stages. And the first step in doing this is to figure out what E1 is. E1 is going to be in equilibrium with R1. So why don't I go back to my equilibrium data and make a plot that's going to be helpful to me. So here we've got our equilibrium data, and we've got our water phase, which is going to be high in diluent. And this means that it is the raffinate phase. And we have our isopropyl ether phase, which is high in the solvent, and this is our extract, because the extract is high in solvent. Now you could choose to plot either isopropyl ether water or acetic acid, but our standard here is usually plotting the solute, which is going to be the acetic acid. So I'm going to plot the acetic acid that's in the raffinate down here versus the acetic acid that's in the extract. So for instance, I've got 46.4, so let's go to that point. It would be here. And the acetic acid in the extract is going to be 0.36, which will be this point right here. And this is what I'm going to be using to determine the amount of solute in the extract if I know the amount in the raffinate. Let's go back here. I know what the raffinate is coming out of stage 1. So I want to find out what the extract is coming out of stage 1. So let's see, the raffinate in the solute is 0.05. So I'm going to make a little thing here, and this is R1, 0.05. It's the weight fraction of solute in the raffinate. I'll go up to my equilibrium data, determine that this is approximately 0.02. That's going to be E1. So if I go here, 0.02 for E1. Now I can find the passing stream, which is going to be R2, using the difference point. E1 and R2 are passing streams. So why don't I plot this? Here I've got my R2. So R2 is about 0.09. I'll go back to this plot and have R2 at 0.09, and we'll go up, we'll go across, and we'll have E2 at about 0.03. So let's plot that, 0.03, that's going to be E2. Then I make another stage. This is R3. R3 is at about 0.013. So we'll do 0.013, which is right here. So this is R3, and maybe that gives us E3 as just a little bit above 0.05. So E3. So this is E3 above here. We'll use the difference point to get R4. And R4 is approximately 0.18-ish. So let's go back here. About 0.18 for R4. We'll go up and across to 0.075 or so for E4. So 0.075 for E4. Now we want to determine what R5 is. Now R5 is at about 0.23. So let's go to 0.23, R5. And this is, the extract will be at 0.1. So that will be E5. It's in equilibrium with R5. So 0.1, maybe a little below 0.1 we'll say, is E5. Maybe we haven't quite gotten to En yet. Note that small changes will make a big difference in the number of stages you need. So try to be as accurate as possible, but you might get different answers from your friends. So R6. So R6 is approximately 0.27. 0.27 R6. And so E6 is 0.13. So 0.13 E6. We have definitely surpassed En, and that's when we know that we are done. And let's talk about why we're done whenever we get an E out that is higher than En. What we're trying to do is pull out solute from this feed stream, and we need to pull out enough solute so that we have an ending concentration of 0.05 in the raffinate stream. The only way we can achieve this concentration in the exiting raffinate stream is by pulling out enough solute. So we have to have En have a certain concentration of solute in it. So we need to have the concentration of En be where we calculate it or higher, so that we have pulled out enough solute from the feed stream so that we have achieved the raffinate concentration specified in the problem statement, which is 5 weight % acetic acid. So this would take 6 stages. Alright, after this screencast I realized that I put some of my extract points on the y-axis instead of on the saturated curve. So this point should actually be right here. This point should actually be right here. This point should actually be right here. We'll make it big, and this point should actually be right here. And I apologize for the confusion. I'm going to X out these points. The other points are in the correct spot already here and up here. Of course, your extract should be on the saturated curve, not on the y-axis. This would make my lines from the difference point be a little bit lower, but I think with an error, everything's fine. Sorry about that mistake. We have part B for this problem. For part B, we want to calculate the exiting raffinate and exiting extract flow rates. All we have to do here is a mass balance. So the overall balance is the stuff going in, which is E0 plus Rn plus 1, equals the stuff out, which is En plus R1. So this is in, and this is out. So we've got 2,500 plus 1,000 equals En plus R1. Now let's do a species balance. We'll do it on the solute, species A mass balance. And that is, again, the stuff going in, E naught Y A naught plus R n plus 1 X A n plus 1 equals the stuff coming out, which is E n X A n plus R1 X A1. And from the plot, we know a lot of these values. 2500 times 0.01, and 0.01 is given in the problem statement, is that the solute or solvent has 1 weight percent acetic acid, plus R n plus 1, which is 1000, XA n plus 1, which is given in the problem as 0.3. That equals En, and we'll just get En from this mass balance up here. So it's 3500 minus R1 times XAN, which is, from our diagram, 0.1, plus R1 times XA1, which is specified in our problem as 0.05. And if you calculate this out, you should get R1 equals 500 kilograms per hour, and En equals 3,000 kilograms per hour. And you are done with the problem.